Let's do a short lesson on the power rule. And some of you are in Calc BC, so you've already had a year of calculus, and you should be very familiar with the power rule. And some of you are in Calc AB right now, and you're probably a month away from learning about the power rule. But I'm going to give you kind of a short version of how you might see it in a calculus class, and then how we'll use that in a physics class. So the power rule is a rule that describes how to find the derivative. And we have to decide what a derivative is. So what is a derivative? And a derivative really is, taking a derivative, or finding the derivative is finding the equation for the rate of change of something. And there's lots of ways to say it. So in a calculus class, we're going to give you some function, and we'll just use y. So y might be some number a times x to some power n. And if we want to find the derivative, meaning we want to find an equation for the rate of change, so we want to find the rate of change for y, we want to find the slope of y. And we're in an instance now where the slope isn't constant, right? We're not talking about lines. We're talking about some polynomial, some x squared, some x cubed, some square root function, where the slope is a non-constant, right? The slope depends on x, right? The rate of change depends on x. Then I want to find a way to find it. So there's lots of different ways we can say this, but the derivative of y in the abstract, what we would say is dy dx. And really, it's really just the operator we're doing. That's the derivative of y with respect to x, meaning x is the variable that we're taking the derivative with respect to, meaning we're looking to see how y changes as we change x, right? That's the slope. That's a way to say it. That's a way to say it. You can even say y prime. Y prime is another way to say it. F prime, df, dx, all of those things are the same thing. All of these notations are just saying find the derivative. So how do we find the derivative of this particular function? Well, it'll turn out, and again, Mr. Gemrick or whoever your calc teacher is will kind of walk you through this, but in a physics class, we're just going to go through the basics here. This coefficient out front here, this a, that'll just chill out, and all we have to do is bring down the power, meaning multiply by the power, and then decrease the power by 1. And that's it. That's the power rule. Now, the power rule is only good for polynomials, square roots, or rational stuff. We'll have to learn all sorts of other rules for what if our function is an exponential, what if our function is a sine curve, a cosine curve, a logarithm, something more complicated than that. But if you have something that's just a x to the n, then all you have to do is bring that power down and then decrease the power by 1. So we'll do a couple examples. So what if it was y equals 4x cubed? Then what's the derivative? Well, the derivative, dy dx, equals, bring down the power, multiply by that, so that's 12x, decrease the power by 1. Okay? What if y was equal to 5x squared? Then dy dx, the derivative of y with respect to x, is 10x. Bring the power down, decrease the power by 1. What if y was some rational expression? What if it was, 4 over x squared? Well, you want to think of 4 over x squared as 4 times x to the negative second, and then you can apply the power rule. dy dx equals, bring the power down, negative 8, decrease the power by 1, and then of course you can rewrite it as something like that. And again, what are these things? Well, these are the equations for the rate of change. This is a way to find the slope of this function at any x value. So let's say I wanted to find the slope at 1. Well, I plug 1 into the derivative, and I could find that the slope was equal to 12. That's the instantaneous slope. That's the instantaneous rate of change. Now, this is all in the abstract. They don't mean anything for us. With this random y function with respect to x. Now, in a physics classroom, The better way is that we're almost always given some x as some function of time or some y as a function of time. So let's say x was 12t squared plus 4t plus 8, something like that. So we have to decide, does the derivative rule, does the power rule work for an extended polynomial? Can I take the derivative? Over here I just showed you the derivative of one kind of thing. But what if I have something and x is a function of this plus this plus this? Well, it will turn out that you can then take the derivative of each piece. So what are we taking the derivative of? Well, we're taking the derivative of x with respect to time, dx dt. But what is dx dt in a physics classroom? Well, what is the rate of change of your horizontal position versus time? Well, that's going to turn out that it's your horizontal velocity. So in a physics classroom, you're not going to see dx dt that much. You're just going to see v. We know that the derivative of x with respect to time is v. And they might not even say time. They clearly know that when you say what's the derivative of position, you get velocity, because you're always going to take the derivative of position with respect to time. And so follow the same rule. Bring the power down, decrease the power by 1. Bring the power down, which is a 1, decrease the power by 1. You can see that the derivative of 4t is just 4. Of course it is. What's the slope of 4t? Well, this is just a line, so the slope of that line is 4. What's the derivative of 8? Well, you don't have to, but you can think about the fact that this is t to the 0 power. And so if you bring that power down, the derivative of 8 is just 0, which also makes sense. What's the rate of change of a constant? Nothing. So of course this doesn't have a derivative. And so you have this. But can you go further? Sure you can. What's dv dt, right? Take another derivative. Well, another derivative of this is the derivative of 24t is just 24, and then the derivative of 4 is just 0. But what is this? Well, this is the acceleration. And so what we have to establish is that in a physics class, we're going to be talking about the horizontal position as a function of time. If I take a derivative of this, I get the velocity as a function of time. And if I take the derivative of that, I get the acceleration as a function of time. And again, finding derivatives is really easy. I'm just using this power rule. Bring down the power, decrease the power by 1. And again, I can do as many examples as I want. Certainly, most of the time, at least early on, you're going to be starting by given the position function, and you're going to take a derivative to find velocity. And again, this is instantaneous velocity. This is an equation to find. That's what the derivative is, right? It's an equation to find the slope. Well, we know that the slope on a position curve is velocity. So if I want to find the velocity at any moment, find the velocity at 0, find the velocity at 1, find the velocity at 5, all I have to do is plug into this equation, right? This happens to be the derivative of this. And then it turns out that if you look at the derivative of velocity, you get 24, which just says the acceleration is a constant. Okay, so these are very much related, right? dx dt is v, dv dt is a. We can even say that sometimes they'll call a x double prime, and so they'll say something like that. So the second derivative of position with respect to time equals acceleration. Right, so this is x prime. Well, then this, of course, is x double prime. Stuff like that. And again, primes are used a little more in a math classroom than a physics classroom. In physics, we just usually name whatever these are. Okay, so this is the power rule going in this one direction. This is certainly what you're going to be responsible for. Eventually, I can make these trig functions, logarithms, and once you learn those rules in calculus, then we can also take derivatives of that in here as well. When we do simple harmonic motion, this is going to be a trig function. Well, then the derivative of a trig function is another trig function, and they get a little more complicated. But at the beginning of the year, this is what you're responsible for. So the hard part is going, not really backwards, but starting with an acceleration. What happens if you don't know the original? What happens if you don't know x, and you don't know v, and you actually were given only the acceleration? Let's say you were given that the acceleration is 12t. What if you knew that was true? What else could you find? And so the question is, what's the reverse power rule? What's the antiderivative? And so they'll use the word integral. integral, they'll use antiderivative, and you're kind of talking about all these things are really talking about the accumulation of things, right? That's what going the other way, right? The accumulation of an acceleration over a time period is a velocity, and accumulation of a velocity is a change in position. And so we have to go the other way. And so think about what the other way goes, right? How does the power rule work in the one case? So if we had like x equals, some random constant b t to the n power, if we looked at the derivative of this, what did we do? We brought down the power and we decreased the power by 1. Well, what happens if you had the velocity or the acceleration? How do you go the other way? Well, instead of bringing down the power, decreasing the power by 1, the other direction, going from v, let's say v was equal to 6t, 6t, how do you find x? Well, now you have to increase the power by 1 and divide by the new power. So increase the power by 1 and then divide by the new power, which gives you that 3t squared. But the hard part is, think about, you don't know this original value. It ends up being some x naught, because the derivative of this would have been 0, and so you can't possibly find the original position knowing this. Again, increase the power by 1, divide by the new power, which is the exact opposite of multiplying by the power and decreasing. So you're doing the antiderivative, so you're kind of doing the inverse operation here. So if we have 12t, we need to increase the power to squared and then divide by 2, so it's going to be 6t squared plus some v naught. And we don't know what that value is, but I know that whatever constant's there, that's what the original velocity is, because when t equals 0, v equals something. Now, what if v naught is 0? We'll find that's just a 0 there, but if v naught was something. So over here they might give you like, what if v of 0 is 10? Okay, so then they're telling you this number is 10. So now you actually know that the velocity function is 6t squared plus some 10. Okay, now go to one more step. What if you knew that the original position was equal to 8? Well then, power rule again, increase this power by 1, increasing this power by 1 makes this cubed, and then divide by the new power, so 6 divided by 3 is going to be 2t cubed, plus increase this power by 1 just makes it a t, plus some x naught. But you know that when t equals 0, x equals 8. When t equals 0, then this has to be an 8. And so now we know that x of t, the horizontal position as a function of time, is t cubed plus 10t plus 8. And again, we've learned the power rule. You can check it. What we're saying is that this red and this v, and lots of times they just say x, v, and a. They don't actually say x of t and v of t, but they are functions, all came from this given. Okay, so what we're saying is, if you had this, if you had an acceleration, and you had some sort of initial condition on your velocity and your position, that these two things can be found. And again, you can't find those things unless you know these two facts, otherwise you wouldn't know those constants. But again, you can always go this way and take a derivative. Take the derivative of 2t cubed. Bring the power down, decrease the power by 1, boom. Take the derivative of 10t, get 10. Take the derivative of 8, get 0. Take the derivative of 6t squared and get 12t. Take the derivative of 10 and you get 0. Remember, this way is derivatives, right? The rates of change of things, this power rule, and then going this way is taking antiderivatives and doing the reverse power rule. Increase the power by 1, divide by the new power. And at this point in your physics career, that's all you need to be able to do for me. You have to understand power rule. You have to understand that taking derivatives, I mean, conceptually, is the definition of velocity. I know that sounds silly, but the definition of velocity is dx dt. It's the rate at which you're changing your position. In this case, we're talking about horizontal velocity because we're talking about horizontal position. Acceleration. The definition of acceleration is the rate at which you change your velocity, right? I mean, these are conceptual facts. That is the definition of what those two things represent. Now, again, they happen to be vectors, and there's all sorts of other things that go with velocity and acceleration, but this is and always will be velocity. Velocity is the rate at which you're changing your position, and acceleration is the rate at which you're changing your velocity. We find those by taking derivatives, but the reverse is true. If I knew an acceleration, I could do an antiderivative to find velocity and an antiderivative to find to this. You know, if we wrote this out using a little different notation, the integral of an acceleration dt is that change in velocity. The change in something's position is the accumulation of its velocity over time. And again, we're gonna have to step out and look at this notation, but at least right now there's only a couple problems in these first sets where you really have to use the power rule. But you know, think about taking the derivative of things and taking the antiderivative of things and using initial values. These are initial values, initial conditions. A lot of people call it an initial value problem. You're going to need those initial values to be able to find these constants. Okay, hopefully this gets you started. Hopefully if you already had Calc AB, this is like a super easy reminder of how certain things are related and how to do certain operations. And if you haven't had Calc AB, you can find me. We can talk more about this, but this will at least get you started on the power rule.